So just kind of looking ahead. With the tests that you took on Thursday and Friday, they take me a long time to grade because literally I have to look at every step and make sure the previous one is equivalent to the one that follows it, and that you're using correct identities. Like everything has to follow one step from the other. So they do take me a little while to grade, and there's a lot of people that have to make them up as well. So don't expect them in the grade book, I'd say, before like Wednesday or Thursday. But I am working like, because I had such a small class on Friday, I think I got like the 16 ones that have taken it so far in here. Like you're graded. First side is good, easy to grade. It's the back page. That was a little more interesting, I think. So looking at the first example here, it says we're switching from verifying or simplifying to now solving. And then again, it shows two different statements. The first statement is an identity. The second statement is an equation. So an identity holds true for any value of x, where an equation is only true for specific values of x. So we're kind of switching from one and moving on to the other. For example 1, it wants us to solve this equation, starting off easy just to get you kind of to have the feel of what we're doing. So we have this equation, 2 times the sine of x minus 1 equals 0. And it says to solve it, writing the specific solutions and then writing the general form. Your book asks for different ways for you to write the answers, and I have that underneath. So like I have the assignment, page 373, 29, and 43 odd, but then underneath it's the same assignment, except the first group you're asked to write it in general form, the second group of problems you're actually asked to find the specific answers. So once we go through a couple, you'll see the difference between the two. Please make sure that you're following the directions and writing them as they're asked to be written, which is why I put it on the board as well. So like if you're solving this equation, what would the first thing that you do to solve the equation? Just thinking algebraically, what would you do to solve the equation? Or what's the goal if you're solving an equation? Greg?
We said
it is equal to 0.
Get their stuff to the other side.
Yeah, so usually you want to isolate x because you're trying to solve for x. So whatever contains the x is what we need to isolate. So that means we have to take everything else to the other side if it doesn't contain the x. And in this case, the sign is what we're trying to get by itself. That's the function that contains x. So we'll take the 1 to the other side and divide by 2. So you're isolating x. Now here's where the unit circle comes in, because now we're trying to find x, which is the angle. So thinking back to the unit circle, remember the sign is your y of the ordered pair on the unit circle. And we need to figure out what angle has a sign value of 1/2 on the unit circle. And there are actually 2. Because sign is positive in 2 quadrants, it's negative in 2 quadrants. Where's the sign positive at? Let's start with that, because we have a positive 1/2. So where's sign positive on? Quadrant 1 and 2. So sine is positive in quadrant 1 and 2. Remember, all of them are positive in the first. Sine is positive in the second. Tangent third. Cosine fourth. So then we need to think of an ordered pair that has a 1/2 as the y value, and then the angle that would be attached with that ordered pair. That gives us the specific solutions from the interval of 0 to 2 pi. So Emma, do you know what the angle would be when sine has a value of 1/2?
Is that 30 degrees?
It is 30 degrees, so can you give it as a radian?
A pi over 6.
Pi over 6. So the ordered pair would be √3 over 2 and 1/2. And that's a 30-degree angle, but we're looking at radian values, so it's pi over 6. We want that same angle on the other side, except it would be negative √3 over 2 and positive 1/2. So Emma, that angle would be
1, 2, 3.
Sean, you want to help her out?
120.
So I want it as a radian value.
Oh, 5 pi over 6.
5 pi over 6, there we go. 5 pi over 6. So those are specific solutions. They must be in radian form. Right here it's telling us they want a value as a radian. And I'm pretty sure all the angles we find will be radians, unless it gives you an angle that's already in degrees for some reason. Otherwise, we'll use the radian values. So then the second part says write the solution in general form. General form means that I should be able to find this multiple of the angle for any times, or the number of times that I want to spin around the unit circle. So I want to get every angle that relates to pi over 6. So if I take pi over 6 and spin around once, I go back to pi over 6, but I now know it's a larger angle. If I spin around twice, if I spin around 3 times, that's what a general form means. So when we write it in general form, we start off with our angle. And then if I want to go all the way around the unit circle and get back to pi over 6, what do we have to do to add to that angle to get back to pi over 6? But have a different value. Emily?
2 pi.
Yeah, we would add 2 pi. We place an n with that because I could do that for any number of times that I want to spin around the unit circle. So any value with a pi over 6 plus 2 pi, or 4 pi, or 6 pi, or 10 pi, or 20 pi, gets me that same angle in the first quadrant, except we've spun around the unit circle a given number of times. Both angles need a specific formula, because the second one is in a different location than the first. So my other specific formula would be with 5 pi over 6. And again, I need to add 2 pi to that angle to get back to that angle. But I spun around the unit circle now one time from that location. So general form has that plus 2 pi n to it. It just says that I can get any angle that's associated with pi over 6 or 5 pi over 6. Specific is the actual values from 0 to 2 pi. Questions? So that one was kind of straightforward, getting x by itself. Algebraically pretty straightforward. So if you look at the second one, this one looks a little more interesting. We want to solve the equation. We have the cotangent times the cosine squared, and that's equal to 2 times the cotangent. Again, directions are the same. Write the answers in specific solutions, so we'll actually find the angles, and then we'll try and write that in general form. Now we have 2 functions that we're dealing with. One is squared. What do you think you would do to solve this one? We could, but we're not going to do that yet. I don't know if we'll need to do that.
We could take the cotangent to the other side.
Yeah, so Gray started with the first one and said set it equal to 0, and I said it's already set equal to 0. Because that one was just one function, we could isolate that one function by itself pretty quickly. In this case, because we have 2 functions, we're going to get them together on the same side and set it equal to 0. These ones are being multiplied. Ben, how do you take 2 cotangent to the other side?
Subtract.
Yeah, you're going to subtract it to the other side. So if that said 2x, you would subtract it to the other side. So now we're subtracting cotangent to the other side. And it's equal to 0. So why does that work? Like, how did that help us? Jake?
You can take out cotangent.
Yeah, we can take out a cotangent now. They have something in common. And if we can take out what they have in common, generally when something is in factored form, we can then solve for each of those pieces. So they both have a cotangent in common. We'll take out a cotangent. Jacob, what is left after we take out that cotangent?
Cosine squared x minus 2.
Yeah, now we have a cosine squared x and a minus 2. So going back to Algebra 2 pre-calculus, we talked about the zero product property. That says if you're multiplying 2 parts together, 3 parts together, the product of them is equal to 0. You're allowed to separate those pieces and individually set them equal to 0 once it's factored. So by factoring this, which is why we want to set it equal to 0, we can then take those pieces and individually solve them. But it must be equal to 0, zero product property. It can't equal anything else. So the cotangent, if this were an x, we'd set it equal to 0. So now we're taking the cotangent and setting it equal to 0. And then you're taking this part here as well, setting it equal to 0. Well, I'm going to just take that 2 over to the other side as well. So essentially, if that were x, we'd solve for both pieces that were x. So now we're solving for both pieces, but they're trig functions. So looking at the one on the left, cotangent is by itself. It's equal to 0. So this is the time where you need to think on the unit circle. When is the cotangent equal to 0? And remember, cotangent is x over y. So going back to the unit circle, thinking about how to get those, cotangent is cosine over sine or x over y. When would the cotangent be equal to 0, Jacob?
Pi over 2.
So he said pi over 2, because the ordered pair of pi over 2 is what?
0, 1.
Yeah, so 0, 1, pi over 2. So x divided by y would be 0 divided by 1. Great, where else?
Negative pi over 2.
Instead of negative pi over 2, what would that value be if it's positive?
3 pi over 2.
3 pi over 2. At 3 pi over 2, our ordered pair is 0, negative 1, and we take x divided by y. We also get a cotangent value of 0. So right now, specific solutions for cotangent would be pi over 2 and 3 pi over 2. Because that's when the cotangent is 0. That's when x divided by y, 0 divided by 1 is equal to 0. Let's look at the second one. We have cosine squared and it's equal to 2. So how do you get the cosine by itself? And
Take the square root.
and take the square root. Since it's x squared, cosine squared, take the square root. So now we have cosine x. Anytime you take a square root, then what goes in front of that number? Plus or minus. That still holds true. There's a plus or minus root 2 there. So now we have to think, when is the cosine equal to positive root 2 or negative root 2? Colleen? So she said pi over 4, which is close. What is the cosine equal to of pi over 4? 10? The square root of 2 over 2. So this is just the square root of 2. Right?
Pi over
He said pi over 8. Cut it in half. Why not? What's the highest value that cosine is on the unit circle? Grant? 1. What's the lowest value that cosine is on the unit circle?
0.
Negative 1.
Negative 1.
What is approximately the square root of 2? More than 1. It's 1.41. So, does that value exist? No. So this one here is undefined because the range for cosine, bless you, is negative 1 to 1. And that is outside of the range. So cosine can't be the square root of 2. There's never an angle that gives us a square root of 2 because cosine goes from negative 1 to positive 1. So this part here doesn't actually give us an answer. It just happened to be part of the equation, but it actually isn't a solution. Questions? So our two specific solutions are these right here. So this is part A. We need to write that in general form, which means if I spin around the unit circle, I wouldn't be able to get that in general form. Emily, what do you think?
X equals pi over 2 plus pi n.
So Emily said x equals pi over 2 plus pi n. Why didn't we say 2 pi n like we did for the previous problem?
Because if you say pi n, then you still get the 3 pi over 2.
Yeah, so because these angles are only a value of pi away from each other, by adding pi, you're picking up that 3 pi over 2. And we only need one general equation instead of having two. There's another reason that happens. What's the period of tangent and cotangent?
Pi.
Pi. So the period of sine, cosine, secant, cosecant is 2 pi, where the period of tangent and cotangent is just pi. That's also why you're really only adding pi, because all those angle values are going to be pi away from each other because the period is pi for tangent and cosecant. Questions? So don't write two general equations if you don't need to. We only need one because by adding pi, we're picking up that other one. All right, so we're going to look at a couple other equations on the next page. So So that first one, pretty straightforward. The second one involved GCF factoring, greatest common factor, taking out what they had in common. What does this one look similar to in algebra? 2 sine squared minus sine minus 1. Emerson. Yeah, that looks very similar to a quadratic equation. So this looks like 2x squared minus x minus 1. Algebraically, it has that same pattern, ax squared plus bx plus c. So Emerson, how would you solve this type of problem? Yeah, probably factor. If you want to factor it with the x's, because you don't like factoring it with sign, that's fine. And I know that's an easy thing to use, factoring it with an x instead of a sign. But it's that traditional factoring AC grouping that we did so much last year. We did a lot at the beginning of the chapter, or I'm sorry, beginning of this year. So Emerson, what would you use here? Yeah. If you want to factor it with the x, that's fine. So take out what they have in common. The second group only has a positive 1 in common. So this is 2x plus 1 and x minus 1. So that's the algebraic. Plug it in sign instead. We've got the algebra. Let's replace algebra with trig. So this is 2 sine x plus 1. And then this is sine x minus 1. It started out equal to 0. It's still equal to 0. We just factored it. So zero product property says once it's factored, you split apart those factors and solve for them individually. So see if you can find the angles associated with both of these pieces. So it just says solve the equation in the interval of 0 to 2 pi. So we want to know the angles that fall in the interval of 0 to 2 pi. Jacob Smith, where's sign negative? Quadrant 3 and 4. And when would it equal to negative 1 half?
7 pi 6.
Nice. So remember, sine is a y. So we have negative root 3 over 2 and negative 1 half in the third quadrant. And then positive root 3 over 2, but still a negative 1 half in the fourth quadrant. And that's 11 pi over 6. So those are two answers that pertain to the first factor. But there's also going to be another answer because we have another factor. Elena, when is sine equal to 1?
Pi over 2.
So right here at pi over 2, that ordered pair is 0, 1. The sign is the y value. So another solution would be pi over 2. Questions? So if we were to write general solutions, you would have 3 separate equations for the general form. This one doesn't ask us to do that. It just says find the solutions within the interval of 0 to 2 pi. But you would have 3 solutions in that form. Questions? So see if you can solve example 4. This one just says to write the solution in general form, so we don't kind of need the specific solutions to get it in general form, but the answer can just be general form.
For like our homework and stuff, do we have to draw pictures?
Mm-mm. No, as long as you have the undergrad support. Any suggestions about how to start this one? Grant, what do you think?
Well, would you add sign X to the other side? Or the negative sign X to the other side?
Yeah, so we can get those signs together. So sin x and sin x make
Two sign X.
2 sin x, yeah. Now it's equal to 0. What did you do anything else?
I wasn't sure what to do here. My first instinct is to square things, but I feel like that's not the right way to go.
Morgan.
You subtract the square root to the other side.
Yeah, so because this is just one function, Grant, you could square things, and like we could square both sides. That just adds things to the problem. We're actually going to do that tomorrow to help us solve. But because it's just one function here, we can isolate that function as if this said 2x. So she said take the square root to the other side. And then Morgan.
Divide everything by 2.
Yeah. So now we have the sine is equal to negative square root of 2 over 2. So anytime you just have one function in the problem, generally get that function by itself. Just like if there's just an x in the problem, get that by itself. And we just said sine was negative in 3 and 4. So it wants general solutions. You still need those specific angles. Morgan, when is the sine negative square root of 2 over 2?
5 pi over 4.
5 pi over 4, what did you say?
And 7 pi over 4.
And 7 pi over 4. So those would be specific. To make it general, because it's sine, you add 2 pi times n. So if I continue to add 2 pi, I'd go back to this angle. That makes it coterminal, but that also uses the period of sine. And then we would add 2 pi times n to the 7 pi over 4 as well. So specific form would be 5 pi over 4, 7 pi over 4. General form is saying I can get that angle for an infinite number of values. As long as I just spin around the unit circle. Might get a little dizzy, but I can still hit that angle again and again and again and again and again. Questions? So then there is one final problem on here. So set up similarly to the first two that we did. Solve the equation, write the specific solutions between 0 and 2 pi, and then the general form. And it never includes the value of 2 pi because that's when the numbers start to repeat. Because 0 and 2 pi have the same values. That's why that number is not included. Sean, what are you thinking for this one?
I move the 1 to the other side first.
And then?
And then divide it by 3.
Yeah. So you're still isolating that one function. It's just one function, so we isolate it. And then what happens?
Square root.
Good. So because the function is a squared term, if it was x squared, we'd have to take the square root. So we have, this is really the square root of 1 and the square root of 3. Sean, do you know what that becomes when you just...
Rationalized it and made it square root of 3 over 3.
Nice. So rationalize that. The square root of 1 is 1. The square root of 3 bumps to the numerator by multiplying by the radical square root of 3. square root of 3 over 3. What's missing?
Plus or minus.
A plus or minus. Anytime you take the square root, don't forget to have the plus and the minus answer. So we are looking for two angles where the sine is, the tangent is positive square root of 3 over 3. And then we're also looking for two angles where the tangent is negative square root of 3 over 3.
Pi over 6.
And why do you say pi over 6?
Because the ordered pair is square root of 3 over 2 and 1/2. And if you put y over x, which is tangent, it becomes. Wait, did I get that wrong? Oh no, I got that right. Okay.
No, you're good.
It becomes
Yeah.
square root of 3 over 3.
Good, no, perfect. So he said tangent is y over x. So the ordered pair that we're looking at, my angles obviously are not drawn to scale. I have them drawn as pi over 3 angles. And I honestly just drew angles to the picture. But so the square root of 3 over 2 and 1/2, tangent is y over x. So 1/2 divided by the square root of 3 over 2 is really multiplying by 2 over the square root of 3, which is how we get that 1 over square root of 3 value, or root 3 over 3. So that is a pi over 6 angle. So the positive solutions, Jacob, would be pi over 6 and 7 pi over 6. The negative root 3 over 3 would be
5 pi over 6 and 11 pi over 6.
right, 5 pi over 6 and 11 pi over 6. So your two positive answers are in the first and the third quadrant. The two negative answers are in the second and the fourth. So that gives us all the specific solutions. There are 4 of them because it's plus and minus. So we have 2 positive, 2 negative. So that would be part A. How about part B, the general form? Remember, this is tangent now. Grant?
So it would be, simple first one would be x equals pi over 6 plus pi n.
Nice. So that then gets that 7 pi over 6 because they are 180 degrees away from each other. And then Grant, the second one would be?
X equals 7 pi over 6 plus pi n.
Not 7 pi over 6 because these guys are pi away from each other. So this first equation gets both of those positive angles.
Oh, okay.
So then we would use,
That would just be the 5 pi over 6.
yeah, the 5 pi over 6 plus the pi n. So
You just-
one equation for the first two angles, because if you add pi to pi over 6, you're going to get that 7 pi over 6. So we get those two values from this first equation. The second equation, the 5 pi over 6, if you add pi n to that, then we get that 11 pi over 6.
So you just need those two.
You just need 2.
Okay.
So because of the pi n, you only need 2 equations. So anytime you have tangent or cotangent, you only need the kind of like the one equation for the group of angles. Any questions? Yeah.
Does it matter if you use the pi over 6 or you use the other?
We try to use the first angle and base it off that first angle because then you're spinning from that location. Otherwise, you'd have to use like a negative for n to get to kind of go backwards to get the other angle. Other questions? So that's actually all I have. We're not going to start the next set of notes. The next set of notes continuing to solve. We're going to start tweaking the information. So it's 8 problems, 29 to 43 odd. Please show work. Make sure you're following the directions. We got about 9 minutes